Hi everyone. Today let's talk about Chapter 8, Graph Theory. 8.1 Introduction, Terminologies and Notations. A graph is a set of vertices and edges. Definition: a graph or directed graph G consists of a set V of vertices, also called nodes, and a set of edges such that each edge is associated with a pair of vertices V and W. If there is a unique edge E associated with the vertices V and W, we write E equals this parentheses V comma W, or we can write E equals the parentheses W comma V. In this context, this parentheses V comma W parentheses denotes an edge between V and W. So this is not an ordered pair. Okay, I know before our notation we use this to denote like coordinates, points, is an ordered pair. But in this context, this guy does not denote an ordered pair. Okay. If a graph G has a vertex sets V and an edge set E, we can write G equals parentheses V comma E parentheses. Okay, so we have saw graph before. Do you remember in chapter 3 when we talk about relations, right? We can have some directed graph. We have the vertex be the elements, and then the relations from A to B, we can draw a directed edge between them. Okay, so directed graphs consider the edge VW as an ordered pair. And on directed graphs, okay, the directed edges are indicated by arrows. So let me give you some example here. We can have like V1, V2, okay, V3, okay. Let me draw here. So here we have 3 vertices. Okay, so let's draw some edge between them. Let's say E1. So E1 is an edge that points goes around V, so it forms a loop. Okay, and then we can also have E2 goes from V1 to V2, and we can have E3 goes from V2 to V1, and we can also have like E4 goes from V2 to V3. So this guy is a directed graph. Okay, and for undirected graph, we just remove all the arrows. So we have V1, V2, and V3. Okay, this is also E1, E2, E3, E4. So you can think about our directed graph, the edge, we have arrows, okay? And then the undirected graphs, the edge, we just remove the arrows. Okay. All right. And through this example, you can see there are 2 edges between connecting the vertex V1 and V2. That's why sometimes the edge connecting 2 vertices might not be unique. So if the edge is unique, then you can write E equals parentheses VW. Okay, but so this edge might not be unique because we can have this picture. Okay. All right. Let's look at more definitions. So this chapter will be very fun. We can draw a lot of pictures, graphs. Okay, loop. A loop is an edge which would denote VV. So we have the vertex V, a loop just go around itself. Okay, connecting itself. Adjacent. 2 vertices V1 and V2 are adjacent if there is an edge V1, V2. Okay, so we have V1 here, V2 here. If they're connecting by an edge, we say that V1, V2 are adjacent. Okay, they're next to each other. Incident. Every edge is associated with two vertices. If an edge E can be written as parentheses V1, V2, then edge E is incident to vertex V1 and V2. Okay, so let's say this is E, then we can say E is incident to the vertex V1, V2. Okay, next, parallel edges. If two edges are incident to the same vertices, two vertices, then the edges are parallel. Okay, back to our example. If we have V1 and V2, and then if we have two edges connecting them, then E1 and U2, they are parallel. Okay, next, isolated vertex. A vertex is an isolated vertex if it is adjacent to no other vertex. So back to our picture, we can draw one more vertex. So you see this vertex V3 is not connected to any other vertex. So this V3 is isolated vertex. Okay, everybody? And next, simple graph. A graph which has no parallel edges and no loops is called a simple graph. Okay, so what we draw here, this guy is not simple. Okay, so a simple graph has no parallel edges and no loop. So for example, you can have a picture like this. This picture, it has no loop and no parallel edges, then this guy is a simple graph. So even though it's not connected, but it's okay. It's still a simple graph. Next, weighted graph. A graph which assigns numbers, so we also call those number weights, to every edge is called a weighted graph. The weight of an edge usually has a meaning. So it could be a distance or it could be time. So usually it has a meaning. Okay. Next, complete graph. The complete graph on n vertices, denoted k sub n, is the simple graph with n vertices in which every vertex is connected to every other vertex. For every V1 and V2, where V1 and V2 are not the same in the set of vertices of the graph, then the edge, so V1, V2, the parentheses V1, comma V2 is an edge in the graph. Okay. So so keep in mind it's a simple graph and is connected. Okay. So like we had here, this guy is not connected, okay? So this guy is simple, but not connected. Okay? To be a complete graph, first, it must be a simple graph. And second, the graph is connected. And then the third, every vertex is connected to every other vertex. Okay, so let's call this 3. So every vertex is connected to all the other vertices. Okay. For example, if what's K3? Well, K3 we have 3 vertices, right? Each vertex is connected to all the other vertices. So it's just give us a triangle. Okay, so far so good. Alright, let's look at this example. Frequently in manufacturing, it is necessary to bore many holes in sheets of metal. Components can then be bolted to these sheets of metals. The holes can be drilled using a drill press under the control of a computer. To save time and money, the drill press should be moved as quickly as possible. Model the situation as a graph. So here we have a sheet of metals with holes for bolts. Okay, and if we draw it into like the graph, well, this is like A, this we call it B, and we have the C and D and E. Then we form a graph. Okay, and you see there are a lot of edges. Okay, there are a lot of edges connecting them, and each edge you can see there's a number over there. So this number denotes the time to move the drill press. Okay, so this guy is a weighted graph. In a weighted graph, the length of a path is the sum of the weights of the edge in the path. Okay, so suppose the path is required to begin at vertex A and end at vertex E. We want to find the minimum length path. Okay, so A is our starting point, E is our terminal point, right? Well, how many paths connecting them? So how many numbers are there? So we have 5 letters, A, B, C, D, E, right? And so we have 5 vertices. Okay, let me draw it here. So we have 5 vertices. All right, we have, so it's like we have 5 boxes. We want to start with A and we want to end at E. Okay, how many different paths are there? Well, here we have 3 boxes. We want to fill with B, C, D in some order, right? And we're looking at the number of permutations because order matters. Well, so number of permutation is the first box we have 3 choices, second box 2 choices, and the last box 1 choice. So that's why we have 6 different ways. So we have 6 different paths connecting A and E. Okay, so let's make a table. Okay, so let's denote, here we have the path, and here let's talk about the length of the path. Okay, and in this case, that's the time to move the drill press. Okay, so we should have 6 paths. So let's see, A, B, C, D, E, right? This is one path. And then we can switch C and D, so D, C here. Then we can start with C, C, B, D, E, and then we can exchange the B and D, so D, B, E. Okay, let's continue. We can start with D, and then C, B, E, and then B, C, E. So those are the 6 possibilities. Okay, and then we want to find out the length. Okay, so let's look at this picture. AB, well, AB is right here. So AB is 8. And then BC right here. BC is 6. And then CD is 3. And then DE is 4. Okay, so what is that? Well, 6 plus 4, 10. 8 plus 3, 11. 10 plus 11, 21. So far, so good. This is 21. Okay, let's continue. A, B, D, C, E. Okay, let me erase the picture now. Okay, so A, B, let's do this one. That's 8. BD, BD, see, is this guy, is 12. And then DC 3. CE is 5. So that's 8 plus 12 is 20. So 20 plus 8 is 28. So far, so good. So, okay, I hope you can like pause the video here and try to figure out the rest. And then after you're done, you can continue to play the video and check our answers. Okay, have you done? Let's see. We have AC. AC is 2. CB. CB 6. BD is 12. Then DE is 4. So we have 4 plus 6, 10. 10 plus 14, 24. Okay, so far so good. Let's continue. Let me see. When I continue, I don't see the graph. Okay. Let's see. Here, ACDBE. Okay, so let's see. ACBDE, like that, right? ACBDE. Oh, we already did this. We want to have ACDBE. ACDBE. Oh, so 2, 3, 12, 9. 2, 3, 12, 9. That gives us 5, 17 plus 9, 26. Okay, next, ADCBE. Okay, keep in mind, ADCBE. ADCBE. So 2, 3, 6, 9. Is that okay? Sorry. Is it 4, 3, 6, 9? 4, 3, 6, 9. So that is 4 plus 6, 10. 10 plus 12, 22. Okay, finally, ADBCE. ADBCE. 4, 12, 6, 5. 4, 12, 6, 5. 4 plus 6 is 10. 10 plus 17, 27. Okay, so that is all of the paths. That's all the possible paths. So far, so good? Okay, now we compare all of them. Which one is the smallest? Yeah, this guy is the shortest. Okay, so here, this way, we list all of the possible paths. Okay, so this way, we list all possible paths. Okay, and we can compare. But however, here we have 5 vertices. If we have 6 vertices, well, how many possible paths are there? You're gonna have 4 factorial, so that is 24. If I give you one more vertex, well, then 24 times 5 is going to be 120. Are you really want to compare 24 paths or 120 paths? So this way is kind of time consuming. Okay, so this is an example. So this is an example of the traveling salesperson problem. Okay, we will talk about that in sessions 8.3. So in this chapter, I will teach you there is an algorithm to find the shortest path. You don't need to list all the path and calculate all the length and compare the shortest. So there is a way, an algorithm to help us to find the shortest path. Okay? All right, let's continue. The degree of valency of a vertex of a graph is the number of edges that are incident to the vertex. Loop are counted twice. Okay, so loop are counted twice. This is so important. The edge of a vertex V is denote the degree of V. Okay, so the degree of vertex V. Yeah. So for example, let's look at the following example. Explain why the following does not have a path from A to A that passes through each edge exactly one time. Okay, so let's look at the degree at each vertex. Well, let's look at A. We have 2 edges connecting it, so degree is 2. How about E? We have 1, 2, 3, 4. So we have 4 edges. D 1, 2, 3. So we have 3 edges. And then C 1, 2, 3. So 3. B 1, 2, 3, 4. So we have 4. So those are the degrees. Okay. Now let's look at this problem. Why this graph does not have a path from A to A that passes through each edge exactly one time. So what is it asking about? So we want to find a path that pass through each edge one time. Oh, you see this path? Yeah, we go from A to A in it crosses all the vertices, but it does not pass through all the edges. Okay. So how do we think about this? Okay, let's see. So if we have a vertex, and when we go through the vertex, we have a path coming in from a edge and going out through an edge, right? So which means each vertex should have an even degree, because you want to come in and go out. If you have an odd degree, you're just stuck there. Right? So we can see each vertex must have even degree. Oops. Okay, because we go in and we go out. So it must be even degrees. But let's look at our picture. A degree 2 is even, E degree 4 is even, but D degree 3 is odd. C is degree 3 is odd. So D, C, they have degree 3, okay, which is an odd degree. So that's why it's impossible. Okay, it's impossible that we have a path from A to A that passes through each edge exactly once. Okay, because the points D and C is odd degree. They come in and they go out, then they come in and they stuck there. Okay. Alright, let's continue. Next example. We want to show that the graph has a path from A to A that passes through each edge exactly one time by finding such a path by inspection. Okay, let's look at the degree. A degree 2, B degree 4, E, D also degree 4, F 2, E 4, C degree 4. Okay, good. So you can see all of the vertices have even degrees. Okay, so let's try to find a path, okay? So let's try A, B, C, D. This doesn't work because we want to pass through all the vertices, right? So let's see. We can do A, B, D, C, E. Okay. And then let's use different color because when I repeat, then you can see the difference. And then we can do F, D, E, B, C, A. Can you see it? In this way, we can pass through all the edges exactly once. Actually, there are more other paths. Okay, let's write down what we have here. We did A, B, D, C, E, and then we do F, D, E, B, C, A. Okay, so this is one path. And actually there could be other path. Let me use a different color. Let's see. We can do A, B, E, F, D, E, and let's change a different color. And then we can do C, D, B, C, A. Okay, you can see this path also go through all the edge exactly once. So this is A, B, E, F, D, E, C, D, B, C, A. Okay, so this is another path. So you can see there could be quite many different paths that pass through each edge exactly one. So the answer is not unique. Okay. So far, so good, everybody. All right. Let's continue in video part B. See you soon.